Okay, so hello everyone. My name is Anudh Mishra, and right now I'm a student at AIIMS Bhuvneshwar, second year student. My rank in NEET 2022 was AIR 87. Today we are going to start with chapter States of Matter. So this is the fifth chapter of your class 11th chemistry. It comes under physical chemistry. First, we'll see a few brief introduction of this chapter, and we'll move on to some previous year questions of JEE-Main. Okay. Chalo. So, introduction. What is states of matter? See, matter exists in different states. Okay. Any matter. For example, water. Water can exist as ice, which is solid. It can exist as a liquid, or it can exist in a gaseous state. Okay. As water vapor or steam. Right. So, ice, liquid water, and vapor and steam. These are the three states of matter: solid, liquid, and gas. Now, most of the observable characteristics of a chemical system with which we are able to familiarly represent bulk properties of matter. Okay. It is the, what are these? They are atomic size, ionization enthalpy, electronic charge density, molecular shape, and polarity. So with these properties, we are able to explain all the observable characteristics of a chemical. Okay. Now, this was the introduction. Why we need to study states of matter? Okay. Because chemical properties of a substance do not change with the change of its physical state. But rate of chemical reactions do depend on the physical state. So, if water is giving a reaction, it will give the reaction in all three forms: solid, liquid, or gas. That won't change. But the rate of that reaction will depend on the physical state. It might be so key in the liquid state, the reaction is happening in the fastest rate. But in the gaseous state or in the solid state, it slows down. That is why we need to know the properties of different states of matter of the properties. These properties will help us to determine which is the appropriate state of matter which we need for a reaction and why is it so. All right. We need to know the laws which govern the behavior of matter in different states, right? That is the importance of this chapter. So we move on to the intermolecular forces. So this is a very important part of the chapter because this is what will decide if a matter will exist in solid, liquid, or gas, the amount of intermolecular forces. Okay. So first we know van der Waals forces. These are always attractive. Okay. They cannot be repulsive. And there are like three types of van der Waals forces. Before that, only a few elements can participate in hydrogen bond formation. So it is treated as a separate category, although it is a part of a van der Waals force. But all of the particles cannot exhibit hydrogen bond. So we learn it separately. Otherwise, in van der Waals forces, we include the London forces, we include the dipole-dipole, and we include the dipole-induced dipole. Right. Okay. So London forces are induced dipole, then we have dipole-induced dipole, and then dipole-dipole. What is a dipole? At first, I'll tell you what a dipole is. Suppose this is a neutral body. Okay. Plus, minus. It is neutral. It has one plus and one minus. Distance between plus and minus is 0. Suppose I distort it in some way and bring the plus and minus at different positions. Then it becomes a dipole with a direction of dipole towards the positive. So we can see here there is a symmetric distribution of electrical charge cloud, so no dipole. But here we can see at B that plus charge has been brought to one corner, so there is formation of dipole. And atom A is the dipole. Atom B was near atom A. So atom A induced a dipole in atom B. Because here it is negative, so it will bring all the positive of B towards its negative, right? And similarly, if atom A ka positive is on this side, it will attract the negative of atom B on that side. Okay. So this is what is happening in London's forces. Both atom and atom B are having symmetrical distribution, but not every time. Okay. Momentarily, electronic charge distribution in one of these atoms becomes unsymmetrical. Okay. This results in development of instantaneous dipole on atom A, which we can see here. Okay, this is a instantaneous dipole. This instantaneous dipole distorts the electron density of other atom B, which is close to it. And a dipole is induced in the atom B. So we can see that atom A is an instantaneous atom which induces a dipole in atom B, right? This is an example of London forces. So in London, what we have to remember, both are not dipole, okay? It is instantaneous dipole, induced dipole. Next, we move on to dipole-dipole forces. It is between two dipoles. We can see here we have two dipoles. They will attract the opposite partial charge on them. So delta plus is partially positive. Delta minus is partially negative. Okay. Then dipole-induced dipole. Here we have one permanent dipole and one non-polar molecule. This permanent dipole will induce a dipole in the non-polar molecule and they will get attracted. This force is known as dipole-induced dipole force. Then we move on to hydrogen bond. So hydrogen bond is basically between, see, there is a X atom with a lone pair and there is a hydrogen atom which is attached to a Y atom. Okay, now this Y atom is electronegativity is very high. So it will distort all the negative charge from the hydrogen. Hydrogen will become partially positive. Okay. Example of Y is fluorine, oxygen, nitrogen, and carbon in sp hybridization. Okay. If hydrogen is attached to these four species, it can show hydrogen bonding. And the example of X is any molecule having negative or lone pair. Any molecule which is negative or lone pair. This partially positive hydrogen will attract the lone pair or the negative charge on this atom, and this is known as hydrogen bond. So what we are doing, we are removing electron cloud from the hydrogen, basically inducing a kind of dipole on the hydrogen, making it positive, partially positive. And this partially positive hydrogen is attracting the electron cloud from other molecule, which is having excess of electron cloud, i.e. which is negatively charged or which has lone pair. Okay. So here we can see HF. Here fluorine has lone pair also and fluorine is electronegative also. So it can exert this dipole forces and participate in hydrogen bond formation. Next, we have discussed only attractive forces so far, but molecules also exert repulsive forces on each other. Okay. When two molecules are brought in close contact with each other, repulsion between the electron clouds and that between the nuclei of the molecules comes into play. Okay. As the distance is reduced, your repulsion increases rapidly. This is the reason that liquids and solids are hard to compress. Okay. Because there are repulsive forces also. Next, we move on to the thermal energy. Thermal energy is the energy of a body arising from motion of its atoms or molecules, it is directly proportional to the temperature, right? So thermal energy is proportional to the temperature of a substance. Now, intermolecular forces versus thermal interaction. So these are two opposite interactions. If thermal energy is more, then intermolecular forces will be overcome by the thermal forces. So this is basically a opposite reaction. Suppose the thermal energy of a body is more. It has some degree of intermolecular forces, but if the thermal energy is sufficient, it can tear the molecule apart, which means it can change solid into liquid or gas, right? But if you reduce the thermal energy, you bring down the temperature. The thermal energy, the vibration of the particles are like getting less and less. Then the intermolecular forces can catch the particles together. That is, you can change a gas into liquid or a liquid into solid. So here we have two small graphs we need to remember. Predominance of intermolecular attraction, maximum in solid and least in gas. Okay. And predominance of thermal energy, maximum in gas and least in solid. So what do we learn from it? Gas has the maximum amount of thermal energy and least amount of intermolecular interaction. That is why it has no fixed volume, fixed shape. It can just expand infinitely into space if you give such a big container to it. Similarly, the intermolecular interactions are the most in solid. That is why it has a fixed volume, fixed shape, and you cannot just distort like that, because the intermolecular forces are so high that they will keep the molecules together. Okay. Next, we move on to the gaseous state. Okay. So this is the simplest state of matter. Okay. Now, best example of gaseous state is the thin layer of air around the earth, which is not that thin. It is really thick for us, sufficient for us to survive. And it is a mixture. We learned in the first chapter, it is a homogeneous mixture of different gases. Now let us focus our attention on the behavior of substances which exist in gaseous state under normal condition of temperature and pressure. So we need to remember hydrogen, helium, all inert gases are gases at normal temperature and pressure. Apart from that, hydrogen, nitrogen, oxygen, fluorine, and chlorine are also gases, right? Now we have some physical properties of gases. They are highly compressible. They exert pressure equally on all directions. They have lower density than solids and liquids. Volume and shape is not fixed. They can mix evenly and completely in all proportion without any mechanical aid. Okay. Forces of interaction between their molecules are negligible. The behavior is governed by some general laws, okay, which are discovered as, we know the general laws which were discovered, which explain their behavior. Okay. What are the properties? Pressure, volume, temperature, and mass are important. Okay, because these are incorporated in these laws. Okay. Interdependence of these variables lead to the formulation of gas laws. Now let us go to the gas laws. First gas law which we will study is Boyle's law. Boyle's law is a pressure volume relationship. Okay. So at constant temperature, the pressure of a fixed amount of gas varies inversely with its volume. So this is the Boyle's law. Pressure is inversely proportional to volume at constant temperature and amount of gas or moles. And this is the curve of Boyle's law. Okay. We can see pressure is inversely proportional to volume. The curve shifts upwards at increasing temperature. And each of these three curves is known as each curve corresponds to a different constant temperature and is known as an isotherm. Okay, so we have three isotherms at three different temperatures, and higher curves respond to higher temperature, right? Okay. Now, if there is one more graph given between pressure and inverse of volume, this is a straight line graph. The slope is directly proportional to temperature. Okay. But at higher pressures, gases deviate from Boyle's law, and under such deviation, straight line is not observed in this graph. This is a small thing which we need to remember. Here we also learn about the definition of density. Density is mass by volume, and if we put it in the equation, we obtain density is equal to mass by K1. So D is equal to M by K1 into P. Okay. This shows that at constant temperature, pressure is directly proportional to the density of a fixed mass of a gas, right? So what does this mean? That at fixed temperature, density is proportional to pressure. If we increase pressure, we are compressing the gas. Temperature is the same. Density should increase. If we are decreasing pressure, we are letting the gas, okay, you move around. So gas will just expand and density will decrease. It will become less dense. That is what the statement is saying. Next, we have the Charles law. After Boyle's law, Charles law explains the temperature and volume relationship. At fixed pressure, okay, at fixed pressure, okay, before we move on to the Charles law, they have given us a small definition of the Kelvin scale. We don't need to remember all this. We just need to remember that the Kelvin scale is called the thermodynamic scale, and Kelvin is equal to degrees Celsius plus 273.15. All right. 273.15. We need to add to degrees Celsius to turn it into Kelvin. Okay. Here, the Charles law says pressures remaining constant, the volume of a fixed mass of gas is directly proportional to the absolute temperature. Okay. Absolute temperature, which means it varies directly with the Kelvin scale temperature, not the Celsius scale temperature, because Kelvin scale is the absolute scale, absolute temperature scale, or thermodynamic scale. This is all the Kelvin scale. Okay. Now, if we go with the statement, then here we can remember this box. V1 by T1 is equal to V2 by T2. V by T is equal to constant if pressure and moles are constant. Okay. So V is equal to K2 into T. The value of constant K2 is determined by pressure and amount. All right. So we can draw graphs of volumes with temperatures, and we get a graph like this. Definitely at the absolute temperature, like at absolute 0 minus 273.15 degrees Celsius or 0 degree Kelvin, the gas will cease to exist theoretically, and it will have no volume. So all these graphs will meet zero volume at 273.15 minus 273.15 degrees Celsius or 0 degree Kelvin. Other than that, we can draw straight lines with the slope directly proportional to the pressures. I'm sorry, slope will be inversely proportional to the pressures. We will learn that later why. Each of this volume curve is called an isobar. Okay. Now, Gay-Lussac's law, pressure and temperature. It states at constant volume, pressure of a fixed amount of gas varies inversely with temperature. This is the thing we need to remember in Gay-Lussac's law. And these are the graphs. Similarly, in the 0 Kelvin, the volume should be 0, the pressure should be 0. Okay. Now, Avogadro's law, it is like equal volumes under equal temperature and pressure have same number of molecules. Avogadro constant, we all know about it. Now we will define STP, standard temperature and pressure will have the same volume. Standard temperature and pressure means 273.15 Kelvin or 0 degrees Celsius and 1 bar. And STP, molar volume of an ideal gas, is 22.7 liters. These two things. Next, we move to an ideal gas equation. If we combine all these three laws together and add a proportionality constant known as R, we will get what is called the universal gas. R is the universal gas constant. We will get what is called the ideal gas equation. Here we have the ideal gas equation. Or PV is equal to nRT. N is the number of moles, T is the temperature, R is the gas constant, PV is pressure and volume. We will use this in various equations. Next, density and molar mass of gaseous substance, we already know. Manipulating this equation, we can get, this is the density and the molar mass correlation. Molar mass is equal to dRT by pressure. Dalton's law of partial pressure, total pressure is the sum of partial pressures of all the gases in the mixture. That is Dalton's law of partial pressures. Now, partial pressures in terms of mole fraction. So partial pressure, suppose P1, there's a container and there is like three gases, P1, P2. They are exerting P1, P2 and P3 pressures. And their mole fractions are chi1, chi2, chi3. So P1 is directly proportional to chi1. So P1 is equal to P total into chi1. So total pressures, if we take the mole fraction of that gas and multiply it by the total pressure, we will get the partial pressure of that gas. Suppose mole fraction of a gas is more, partial pressure exerted will be more because that gas is more in amount, right? Mole fraction is more means the gas is more in amount. Okay, next we move to the molecular theory of gases, kinetics. Okay, there are assumptions and then there are theories which explain why real gases deviate from ideal gas behavior. So here we need to remember that what assumptions we have taken. Okay, gases consist of ideal particle with small volumes. There is no force of attraction between the molecules. They are always in constant and random motions. They move in all possible directions in straight lines. Okay, collision are perfectly elastic. At any particular time, they have different speeds and different kinetic energies. Total is zero. If a molecule has variable speed, it must have variable kinetic energy. Okay, average kinetic energy is directly proportional to temperature. So this is what an ideal kinetic theory assumes, but this is not what a real gas shows. That's why the real gases deviate from the ideal behavior. Okay, the curves which we just saw, if we draw a PV versus V curve, we should get a flat line which is of an ideal gas, but we don't get it so in case of real gases. Real gases, as you can see, carbon monoxide, CH4, hydrogen, helium, they are deviating from this flat straight line. Okay, and if we do the pressure volume, the ideal gas and the real gas, they are deviating from each other. At low volumes or at high pressures, at low volume or at high pressures, the real gas is having a much higher volume than the ideal gas. If you increase the pressure, the real gases are not getting that much of compressed because in ideal conditions, we have assumed that their volume is zero, so they can be compressed. But real gases have some volume of their own. So you increase the pressure a lot, which means you take this graph up and you can see that the volume of a real gas is theoretically more, it's practically more than the ideal gas which has been expected. Okay, these two explanations, we move on to a correction term for the ideal gas for the real gas to turn it into ideal gas. So we have a pressure correction term and a volume correction term which creates this real gas equation. Pressure correction term is an square by v square. A is a constant. Volume correction term is nb, which b is a constant. This is the van der Waals equation, and we will use this for different results. Here we define a compressibility factor Z, which is PV by nRT. For ideal gas, Z is equal to 1. Okay. And at high pressures, all gases have Z equal to more than 1 because they are difficult to compress. At intermediate pressures, most gases have Z less than 1. Okay. Now, we go to liquefaction of gases. Liquefaction of gases, we need to understand this curve, one curve which has been given to us. This colored portion of the curve, the dome kind of curve, which we can see, this is the portion where gases exist both in gaseous and liquid state. Okay, basically this is the boiling point of the gas. Okay, so as if we can see these straight lines denote that the gas is boiling here, and it is going to exist in both liquid and solid state. Right side to this dome, gases only exist at liquid state. Left side to this dome, they only exist as very sorry. Right side they exist as only gaseous. Left side they only exist as liquids, and liquids are showing straight lines with PV. We can see these kinds of straight lines in liquids. Okay, I'm going to erase all of this. I'm going to explain this temperature वगैरह correlation for you guys. As you increase temperature, the gases fail to, they fail to come to your liquid point because temperature is so high that they can never exist in liquid. These are the temperatures. This 31, 50. You can see these curves, they never pass through this dome wala phase. They're only coming from below, they're only climbing above. So there is no straight line wala path here. So no liquid phase for these two temperatures because they are high. The first temperature which just touches this dome, okay, it is 30.98. It is known as the lowest temperature which is required to see liquid phase of this gas, and it is called the Boyle's temperature or the Boyle point. Okay, the temperature at which real gas obeys ideal gas law over an appreciable pressure range is Boyle's temperature. Okay, I'm so sorry, this is not the Boyle's temperature, this is a critical temperature. We were at liquefaction, so this TC is known as the critical temperature. It is the highest temperature at which liquid can be observed. See, it is the highest temperature at which it is just touching the dome at this point. So we will just see liquid at this temperature. This is the highest temperature. If we go higher, we will just get these gas wala curves, this curved wala curves. Okay, at 30.98 degrees Celsius and below, for example, 21.5. Let us view this curve. 21.5, it comes from A to B. This is gas. B to C, it is boiling, where both gas and liquid are present. And above C, like we have decreased the volume so much that above C, on increasing pressure, we only get your liquid. This is all a thing of pressure and volume. The more pressure you apply, the more chances of getting a liquid you have. Only if you have crossed the critical temperature. If the temperature is more than critical temperature, no matter how much you're compressing the liquid, how much pressure you are applying, it will not give you any liquid from gas. That is what I was about to tell you, that critical temperature is the highest temperature at which liquid CO2 can be observed. Above this temperature, it is always gas. Volume of 1 mole gas at critical temperature is called critical volume, and pressure is known as critical pressure. So these three are critical constants of a gas. And the TC for CO2 is 30.98. So they have explained what happens at 21.5 degrees Celsius. Carbon dioxide remains a gas only up to point B. Only up to point B. At point B, the liquid of a particular volume appears. Further compression does not change the pressure. Liquid and gaseous carbon dioxide coexist. Okay, just as I told you, both liquid and gas will be there. Until point C is reached, at point C, all the gas has been compressed, condensed, turned into liquid, and further application of pressure merely compresses the liquid. Okay, this is the isotherm that we have explained, right? This is really important that we need to know what the critical temperature is, because otherwise we will just generally think that we can just compress any gas at any temperature and we will get liquid. No, it should be below the critical temperature for the gas to pass through this dome. Okay, critical temperature, it just touches the dome. Below that, it will pass through the dome and we will see both gas and liquid phases at a point. Okay. Okay, there is continuity with the gaseous and liquid state, the term fluid. Okay, so they have given one more think it is possible to change a gas into liquid or liquid into gas by a process in which always a single phase is present. So we how to turn a liquid or a gas into a liquid without going through the phase of that dome, without going to a phase where both of them are present. We can move from point A to F vertically by increasing the temperature. So what they are doing, I'll draw it with I think a green marker for you to understand. They are going directly from A to F for the gas. They are increasing the temperature from 21.5 to 31 degree Celsius. And then they compress the point till G. Okay, they move to from F, they move to G. They compressed, they increase the pressure. And at G, what they will do? They will come down to D. And at D, what do we know? That at D, it will be liquid because the isotherm of the D says that the gas is liquid phase in D. Right? So we can come towards D by lowering the temperature and we can directly get liquid from gas by this process. Okay. So what can we say? There is a continuity between the gaseous and liquid state. The term fluid is used to denote either of them. Okay. Thus, a liquid can be viewed as a very dense gas, and vice versa, a gas can be viewed as a very less dense liquid. Liquid and gas can be distinguished only when the fluid is below its critical temperature and its pressure and volume lie under the dome, since in that situation, liquid and gas are in equilibrium and a surface separating the two phases is visible. Apart from that, we only have gas or we only have liquid. A gas below critical temperature can be liquefied by applying pressure and is called vapor of the substance. Okay, that is, we know what is vapor is. What we always dream, what is vapor? What is the difference between gas and vapor? Vapor is such a gas which is below its critical temperature, so that if you apply a pressure, it will pass through that dome and it will turn into liquid. Okay, that is vapor. So we move on to liquid state now and we move on to the vapor pressure. So what a vapor pressure is, it is, suppose you fill a liquid in a container. I'll just give a small brief. Closed container, you fill it with liquid. You fill it with liquid. Here you have liquid. Some amount of liquid will evaporate. Some amount of liquid will condense. So there will be an equilibrium between the evaporating and condensing liquid. So there will be some vapor present here. And as we know, vapor is gas. It will exert pressures on the container walls. That is known as the vapor pressure. Simple. And here we have a vapor pressure versus temperature curve for common liquids. As you can see, they are not ideal. It is not a straight line, right? Okay. No need to remember this vapor pressure. We just need to know its definitions, right? Boiling does not, we just need to know this. Boiling does not, I'm so sorry. Boiling does not occur when liquid is heated in a closed vessel. Okay. On heating, continuously vapor pressure increases. At first, a clear boundary is visible between liquid and vapor because liquid is more dense than vapor. As the temperature increases, this boundary is gone and everything turns into vapor. For boiling, you need to bring the liquid to atmospheric pressure, expose it to atmospheric pressure to see that big bubbles or boils. Okay. Now, what is surface tension? So, surface tension is the surface of the liquid is pulling itself downwards. Why? Because we can see the attractive forces result in a downward pull. And in this liquid particle inside the bulk, no attractive forces is there. But at the surface, all have a net attractive force towards the bottom or towards the center of the thing. So if we take a bubble, the surface tension will be trying to compress the bubble. That is why if you cannot see a drop of water in a square shape, because these are a bit, the ones at the corners will tend to cause it into a circle. That is what surface tension is. Surface tension is the force acting per unit length perpendicular to the line drawn from the surface of a liquid. Okay, it has dimensions of kilogram per second square, or the term is Newton per meter. At the lowest energy state, the liquid will be when the surface area is minimum. Surface area, if you turn it into minimum, surface energy will be minimum, surface tension will be minimum. Liquid tends to rise or fall in the capillary because of surface tension. This is all physical. This is all you'll study in physics. Okay. Next, we move to viscosity. Viscosity, you only need to remember this viscous force wala formula. Okay. And this is the end of the chapter. We move on to the questions. Okay, first question we have, firstly, we'll see previous year January questions, and then I have some other questions for you also. We'll try to solve them. Okay. Okay, physical chemistry. Following figure shows spectrum of an ideal black body at 4 different temperatures. Okay, so we have wavelength versus energy. So black body is a substance which will emit as much radiation as it is absorbing. This is basically not a question of your states of matter. Still, we'll just try to solve it with whatever knowledge we have right now. Okay. So T4, T3, T2, T1, they have said key the fourth temperature is the highest, because if we take the same energy distribution, the wavelength emitted from the fourth one is the highest, and wavelength, if it is the highest, then the energy is lowest. So this is the wrong statement. Next, the black body consists of particles performing simple harmonic motion. I don't think so. This is also incorrect. Peak of the spectrum shift to a shorter wavelength as temperature increases. Yeah, that we can see. We can see that the peak is shifting to a shorter wavelength as temperature is increasing. This is absolutely correct. T1 by V1 is equal to T2 by V2 is equal to T3 by V3 is not constant. So they are saying that gas laws are invalid for a black body. What do you say? I say it is absolutely correct. They are gas laws. They don't hold true for a body. Then the given spectrum could be explained using quantization of energy. See, quantization of energy says that energy is equal to n lambda, and we can easily explain the spectrum based on quantization of energy. So we get our correct answers. Okay, next, the number of statements which are correct with respect to compression of carbon dioxide in the Andrews isotherm. So this is the dome wala part which I was talking about, and we have to say correct statements regarding to this. Carbon dioxide remains a gas up to point B. It is absolutely correct. This is gas, this is both, and this is only liquid. Carbon dioxide liquid appears at point C. This is incorrect. It appears at point B only. From point B to C, as we know that both of them exist in, like, there is an equilibrium between the gas and the liquid because it is in the dome, so both will coexist. Liquid and gaseous carbon dioxide coexist between points B and C. Exactly, this is what I was talking about. D point, as the volume decreases from B to C, the amount of liquid decreases. How is that possible? From B to C, actually all the gas is being converted into liquid. So we should say that the liquid is increasing in amount. So this is also incorrect, right? So this Andrews isotherm is the only thing which is relevant in this chapter. I know this black body was a bit, out of the box for you, but this will be taught in physics basically, so don't need to worry. You just need to take this back from the chapter. No one should be like, you should be thorough with this isotherm and its properties. Oh, we have one more question. For 1 mole of gas, the plot of PV versus V is given below. P is the P is the pressure and V is the volume of the gas. And we know that this straight line is for the ideal gas we had seen. What is the value of compressibility factor at A? Compressibility factor at A, it is below the, okay. Compressibility factor is Z, which is PV by nRT. This is what compressibility factor is. So At A, which means at lower pressure, your pressure is less. We had just try to imagine at less pressure, the compressibility factor will be what? What can you neglect? See, P this into V minus NB is equal to nRT. This is the real gas equation. This is the pressure correction terms. This is the volume correction term. The pressure correction term says there is a force of attraction, which is why we need to, add a bit more pressure. Then volume correction term says there is a net volume of gas. At low pressures, which of them is negligible? Like pressure is very less. Okay, we just see at high pressures, which of them should be negligible? At high pressure, we can just remove the force of attraction because they are at so much high pressure that this small correction term will be of no use. So similarly, at low pressures, we can just remove this term. So if we remove this term, this comes as PV plus N square A by V is equal to nRT. This is what the thing is. And if we remove N as 1, so PV plus A square by V is equal to RT. So we need to just we take PV common, PV 1 plus A square V square into P is equal to RT. We take RT below. So P by RT is equal to 1 plus, why did I square this? A by PV square. And PV square is equal to, because we know PV is equal to RT, so PV square is equal to RTV. We have our answer. All right. Okay. So that was all, guys. We will go on to a few more questions. Here, question number 3, it says kinetic theory of gases proves. Okay. Kinetic theory of gases proves all of these because kinetic theory is derived from all three. Boyle's law is P is inversely proportional to V. Charles' law is V is proportional to T. And Avogadro's law is Na wala law. So all of these are valid. Next, the heat required to raise temperature of a body by 1 Kelvin is called, we know it is the thermal capacity. This is basically dealt in thermodynamics. No need to worry. Just try to remember it, that the amount of heat that is required to raise the temperature of a body by 1 Kelvin is called, see, amount of heat. There is thermal capacity, then there is specific heat and all of this. So specific, I'm so sorry. I was saying key specific heat and thermal capacity. What do they mean? First, we'll see specific heat. So specific heat, according to specific heat, it says the amount of heat required to increase the temperature by 1 Kelvin for a unit mass. So we just take a unit mass and we raise the temperature by 1 Kelvin. Okay. The amount of heat energy is specific heat. It is specific. Thermal capacity is for any amount of substance. So we just take any amount of substance, we increase the temperature by 1 Kelvin, and the amount of heat energy is the thermal capacity of that body. So basically here they have not written specifically, they have not mentioned unit mass. So mass is not unit, it can be any mass. So specific heat we will remove. Thermal capacity we will put as the answer. Water equivalent is, suppose you are checking thermal capacity of glass, 1 gram of glass or 10 gram of glass. You put some amount of heat to raise the temperature by 1 degree. Okay, so for the same heat energy, if you take the same heat energy and same amount of water, how much temperature will increase? That is the water equivalent for the glass. Okay, how much glass is equal to water, or how much water is equal to glass if you are going to provide the same amount of energy changes. Okay, now fifth question is, sodium and magnesium crystallize in BCC and FCC crystals. The number of atoms in sodium and magnesium present in this crystals are, oh, this is solid state. Okay, solid state BCC and FCC is like body centered cubic and face centered cubic. So see, the thing is, it has not been taught to you. Answer is 2 and 4. I'll just try to simply explain what BCC and FCC is. If you take a cube, suppose you take a cube. Okay. This is a cube that you've taken. And you try to put atoms at the 4 corners. Or sorry, at the 8 corners of the cube. This is a simple cubic crystal. Here, there is no atom inside the cube or on the faces of the cube or on the edges of the cube. There is only atoms at the corners. How many atoms will be there in one cube? So each corner, you can see if there is a sphere and you take it, you keep it on the corner of this thing, your cube. How much of the sphere will be accommodated? 1/8 of the sphere will be accommodated. Because you need to, if a sphere is there, you need to put 8 such cubes in order to cover the sphere fully if you're keeping it on corner of each sphere. So here 1/8 of cube is covered by a sphere. So there are 8 spheres. So 1/8 into 8 spheres. So 1 sphere in total is there in 1 cube. Okay, 1 molecule can be accommodated in simple cubic structure. Now I will remove all of this and I will tell you what a body centered cubic is. In body centered cubic, nothing. In the center of body, you place one more cube. So in the center is there, and then there are 8 on the corners. So 1 plus 1 at the center. Okay, because 1/8 into 8 plus 1 at the center, it gives 2. This is BCC. What is FCC? FCC says, instead of the center, you put the things at the centers of faces. It is a bit difficult arrangement, but how many spheres? If you put it on the center of the face, so you will just divide a sphere into 2. So 1/2 of a sphere you are incorporating. So 1 to you will have it from the corners. Okay, 8 corners. Now 1/2, how many spaces are there? 6. So plus 1/2 into 6, that is 3. So 4 atoms will be there in FCC. That is why I gave 2 and 4. How many unit cells are present in a cube-shaped ideal crystal of NaCl of mass 1 gram? This is also, we'll skip this because it comes under solid state. Okay. This is important, kinetic theory of gases. Ideal gas between two successive collision, a gas molecule travels in. Remember kinetic theory of gases, what it says? The kinetic theory of gases, we had assumed some postulations, and these postulations said that all collisions are elastic and the gas travels in straight path after, before, and every time in between these collisions. So the answer is straight line path. All right. So we have finished all the questions. We will move on to the summary of the chapter to revise what we have learned. Okay. Intermolecular forces operate between the particles of matter. These forces differ from pure electrostatic forces, and They also do not include forces that hold atoms of covalent molecule together through covalent bond. They are intramolecular. Competition between thermal energy and intermolecular interaction determines the state of matter. Bulk properties of matter, such as behavior of gases, characteristic of solids and liquids, they depends on particles in it and type of interaction between them. So if a particle is solid, the kind of interactions will be different, which will be seen for a gas. Now, chemical properties do not change with the change in state, but the reactivity or the rate depends on the physical change, which we already discussed that. Yes, the chemical properties will be same, but the rate at which the reaction occurs, it will be dependent on the pressure, on the state of matter. Okay. Moving on. Forces of interaction between gas molecules are negligible and are almost independent of their chemical nature. There are no negligible forces of interaction between gases. Interdependence of some observable properties, pressure, volume, temperature, mass, leads to different gas laws. First law was Boyle's law, which keep the temperature constant, pressure is inversely proportional to volume. Next, you have the Charles law, which is the isobaric, or pressure is constant, volume is directly proportional to absolute temperature. Now, this absolute temperature is important because it is always represented by the Kelvin scale, which we need to remember. Then we had Gay-Lussac's law. Gay-Lussac's law was at constant pressure, volume is directly proportional to absolute temperature. Combining all three laws, we found out P1 V1 by T1 is equal to P2 V2 by T2. And if we also include the moles and the matter of the gas, which is the Avogadro's law, okay, we will get ideal gas equation, which is PV is equal to nRT. R is the universal gas constant, and this is ideal gas. Adding some correction terms, because this ideal gas, all the real gases do not show ideal gases. They need some correction terms. We have a pressure correction terms, which accounts for the intermolecular forces, and a volume correction term, which accounts for the volume of the gases. The modified ideal gas equation is formed, which is T plus AV AN square by V square into V minus NV is equal to nRT. Okay. Now, at high pressure and low temperature, these forces start operating strongly between gases and they come close to each other and form liquid. At suitable temperature and pressure conditions, gases can be liquefied. Liquids may be considered as continuation of gas phase into a region of very small volume and very strong intermolecular attraction. Some properties of liquid, example, surface tension and viscosity, are due to strong intermolecular forces of attraction. So we had seen viscosity. This force of viscosity is eta A du by dz. So eta is the coefficient of viscosity, A is the area of contact between the two layers, and du by dz is velocity gradient or change in velocity with the height. Here we can see du by dz, dz is the small height and du is the small change in velocity. We need this gradient for calculating the force of viscosity. We need the coefficient of viscosity. Apart from that, we also need the area of the plate. Okay. This is only possible to calculate in the laminar flow. Laminar flow is all of the liquid is flowing in layers one above each other. If there is a turbulent flow, there are no layers, the calculation of viscosity will be very tough. When you move on to the surface tension, I explained what surface tension is, and vapor pressure. These are all properties of the liquid state. This will be taught very well in the chapter liquid state in class 12th. Solid state has not been covered here, but although I gave you some questions, I gave you a little bit of hint on solid state. Even the black body was a bit new for you guys. Anyways, that is the black body thing is going to be covered under physics, thermodynamics. There you will study about black bodies and their properties very well. For now, you just don't need to remember that. For now, if anything is important, it is this curve. I'll just erase it and once again tell you the characteristics. This curve is the Andrews isotherm, and it defines the critical temperature and critical pressure and critical volume for a gas. Basically, you need to know what a critical temperature is. Below this temperature, you might be able to compress a gas into liquid, but above this temperature, there will be no liquid formation from the gas, because it won't just happen. There is no dome, there is no equilibrium, there is no liquid and gas phase. Below this temperature, if you are wondering why this B to C line is straight, it says that the gaseous and the liquid states are in equilibrium with each other. So they coexist independently at equilibrium. All right. That is why you need to know this curve, because although this curve is, natural, you can manipulate the curve and form liquid from gas. All right. Moving from A to F, then from G and going down to T. All right. So that was all. Thank you very much.